Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem sort an array. Basically, we're given an integer array of nums and we want to sort it in ascending order using an algorithm of our choice, but there's a restriction in that we can't use any built-in functions. So you can't just call sort on the input array and then return it, though that probably will pass on Leetcode. In this case, we also want to solve the problem pretty efficiently in n log n time. There's a few algorithms that can satisfy this complexity. The most famous ones are merge sort and quicksort. Both of these are recursive algorithms. Well, merge sort runs in n log n time. Quicksort on average will run in n log n time. In the worst case, I think it can be n squared. In the best case, it can be n log n, but usually people will assume that quicksort is an n log n algorithm. Now, there's actually a third approach as well, which is called heap sort, which runs in n log n time usually. Basically, you build the heap given all of the items, and then you keep popping them in descending order, well, ascending order. And popping will take log n time, and doing it n times will be n log n. That's using heap sort. I think you can also do it with a binary search tree, but I think these are enough options for us to choose from. I'm going to go with merge sort, though I encourage you to try out these other approaches. I think merge sort is one of the more difficult ones among this list, but I guess it's up to personal preference. Also, the quicksort approach does not pass on Leetcode, at least for me, the way I wrote it in Python. Focusing now on merge sort, the idea is that we're given an array, and we want to take a divide and conquer approach. So we could take this entire array and sort it. There's many algorithms that will work in n squared time. But if we break this problem up into subproblems, like we split the entire array into two equal size halves, and then we sort these independently, this is actually more efficient. This will work in n log n time. Let me show you exactly how. So in this case, we have 4 values, so we're going to split them into 2 halves of size 2 each. Now, if we had like an odd number, if we had 5, well, it doesn't really matter too much in that case. We'll put 2 on one side and then 3 on the other side. But we're going to keep doing this recursively, just like this. And then recursively for these, we're going to break them down into 2 halves as well. So put the 5 over here and the 2 over here. And we keep doing this until we can't do it anymore, which now we basically can't, because now we have individual values. We can't really split these up anymore. This is going to be our base case. Now with merge sort, the easy thing is getting to the base case. Afterwards, though, we do the second step. This is called the divide step. It's pretty simple. We just take an array and keep splitting it into halves until we can't do so anymore. But now the second step is the actual conquer phase, where we're actually going to be performing the merge of merge sort, which is when you have 2 individual elements, it's pretty dang simple to merge these in sorted order. We just compare to find which one is smaller. If they were equal, well, then it wouldn't matter. But in this case, 2 is smaller than 5. 5 is greater. So how are we going to merge these two? And when I say merge, I mean we're going to be at this step where we recursively divided this into half. We returned a 5 up here and we returned a 2 up here. Now we want to merge these. We take the smaller one, 2, and we basically swap these 2 values. So now this subarray, which was originally stored over here, by the way, is now going to look like this, 2, 5. And same exact thing on this right side. We return the 3, we return the 1. Now, which one of these 2 is smaller? The 1 is smaller, so it should go first. So 1, 3. When we say this, these values are actually going to be stored here in place, because we only have one single array. We're not creating copies of it when we go and split these up. But now when we take these and we return up to our parent, we're not actually returning these values. Like I said, we're going to be merging in place in this thing. Now that we're going to be merging 2 arrays that are greater than of size 1, it's becoming obvious that to merge them in place in this memory, we are actually going to have to allocate extra arrays. So when we do the merge step and we return up to our parent here and here, we're going to create temporary arrays of this and this. This will make more sense, by the way, when we actually code it up. It's not as complicated as it may seem. But now, to actually merge these two, it's going to be a bit more interesting because it's not just one value each. We're going to use a two-pointer technique. So we're going to have one pointer at the beginning of this array and one pointer at the beginning of this array and a third pointer actually at the beginning of this array. So here is where we're going to decide which value to put. And of course, we want to put the smaller value. So compare 2 and 1, 1 is smaller. So we put a 1 over here. Then we move our pointer over here. And since we've used the 1 over here, we also shift this pointer to now be over here. Now, which one of these two is smaller, 2 or 3? Well, it's going to be the 2. So we put the 2 over here and take this pointer and then shift it by 1 over here and take this pointer and shift it by 1 over here. Now, again, just repeat which one of these two is smaller. 3 is smaller, so we put the 3 over here, and this pointer is going to be now shifted over here. It's out of bounds at this point, so we would basically just fill the rest of the array with values from over here. So we're basically just going to now put the 5 over here, and that's our entire array after we have sorted it. So it's that simple. Now we're going to get into the code, but quickly, why is the time complexity of this n log n? Well, there's two phases here. One is actually dividing the array into sub-problems. How many times can you take an array of size n and divide it by 2 until we get to the base case where we have arrays of size 1? How many times can we do that? In other words, how many levels are going to be in our tree? Well, by definition, what we are asking is 2 raised to some power, let's call it x, is going to be equal to n. Well, what we are asking is n divided by 2 times 2 times 2 times 2, however many times we're dividing this by 2, which is, in other words, 2 to some power called x. How many times can we do this until this is equal to 1, until n has been divided so many times that it's equal to 1? Well, you rearrange this math equation and basically take the log of both sides, and what you will get is log n is equal to x. That basically means that the height of this tree is going to be log n. Okay, well, what's the time complexity of each level of the tree? In other words, what's the time complexity of performing a merge for an entire level? Well, look at every single level. How many values are in this level? 5, because we have each individual value. Well, 4 values. I counted that wrong. Sorry about that. And how many values are in this level? 4. How many values are in this level? 4. There's going to be n values at every single level that we're going to merge. So the overall time complexity of a single level is going to be big O of n. How many levels do we have? We have log n of them. So you multiply those two together and the time complexity becomes n log n. So now let's code it up. So we know that with merge sort, it is a recursive algorithm. So I'm going to define a function called merge sort, which is going to take in some array. And I'm going to use a couple indices, left and right, to determine what portion of the subarray are we now running merge sort on, because we know we're going to keep dividing this. So to do it in place, we can use pointers. We could have alternatively created copies of this array or created subarray copies, but this will save memory. So the main base case with merge sort is, what if the size of the array is 1? That would happen if the left pointer became equal to the right pointer. In that case, we would just return, and I'm just going to return the array. Otherwise, we actually have to do some recursion, which is we want to run merge sort on the left and right half of the array. How do we do that? Because we have to supply the array and we have to supply the left and right boundaries of what defines this subarray. So if we want the left half of this array, we would take the left index and say that's the left boundary, but we'd also need the middle boundary, which is somewhere in between left and right, probably halfway in between, which we can get just like this. Mid is equal to left plus right divided by 2. This is integer division in Python because an index is going to be an integer. And then we also want to call merge sort on the right half of the array. So for the left boundary, we're going to say m plus 1 because the left half was from left up until mid. So the right half is going to be mid plus 1 up until the right boundary. So after we run merge sort on the left and right half, it's going to get to the complicated part, which is merging. But I'm going to use a helper function for that just to abstract a bit of stuff for us right now. We're going to pass in the array into our merge function. We're going to be merging these two halves. So to pass in the necessary information here, let's also pass in the left pointer. And for convenience, we'll pass in the mid pointer as well, even though given the left and right pointer, this function could compute the mid pointer, but this is just a bit easier in my opinion because we already have it here. So might as well just pass it in. And after that's done, we know the array will be sorted, so we would return the array. Now, to actually run merge sort, we would call it on the input array, which is called nums, and we would pass in the left and right boundaries. Left is going to be 0, the right boundary is going to be the length of the array minus 1, and this itself will return the array, so let's just return this, and that's pretty much the solution, but we forgot about this merge function. But this is so modularized that merging is now basically its own Leetcode problem, and I would say it's a Leetcode easy, though it's a bit tricky, so let's make sure that we're careful. We're given an array, we're given left, middle, and right pointers. The reason I have these as capital because it's going to be kind of hard to distinguish between a left and a 1. So hopefully this clears things up. What we want to do now is take the left half of the array and the right half of the array and merge them. So first, let's get the left and right halves of the array. We're going to have to create copies of them. I'm going to call them left and right. So to get the left half, I'm going to say the array from the left pointer up until mid plus 1. The reason I'm saying mid plus 1 and not mid like we did over here is because this is non-inclusive in Python. That means this array will go from the left index up until the middle index and then stop. It won't include m plus 1. Now the right half of the array is going to be starting at m plus 1. This is inclusive, so it will include the m plus 1 that this won't. And then it'll go up until the right pointer, but this way it would not include the value at the right pointer. So here we actually want to say plus 1, and also this should be a capital, but plus 1 so that we actually include the right value. So with these copies of the left and right halves, now we can actually merge them without overwriting any values. If we tried to do this without creating copies, we would possibly overwrite the values that are already there. So now we're going to have 3 pointers like I talked about. I pointer is going to be for the array, and we're also going to have j and k pointers for the left and right half. So our I pointer is going to start at index L in our array, and j and k are going to start at 0 to indicate that these pointers are going to be at the beginning of these two subarrays, of these two copies of those subarrays. Now for the actual merge, the easiest way, in my opinion, to do this is to say while our j pointer is in bounds, j, remember, corresponds to the left subarray, and while our k pointer is in bounds, which corresponds to the right subarray, while both of the pointers are in bounds, we're just going to compare them, figure out which one has a smaller value, and then insert that value into the input array. So if the left value is less than or equal to the right value, we say equal because if they're equal, it doesn't really matter which one we put. If this is the case, then the left value is going to go into the array. So we get the left value from index j and put it into the array at index I. This is probably the most confusing part because there's so many pointers and they look similar. But if we do this, we also want to increment the j pointer. So we do that. And we also want to increment the I pointer. But as I'm going to show you, we're going to be incrementing the I pointer regardless of which condition executes. So I'm going to save that for the end. Now, the else case here is that if the left value was not smaller and it was not equal, well, then that must mean the right value was smaller. So we would basically take this, I'm just going to copy and paste it and just change it up a little bit. So the value here that we would put now would actually come from the right subarray because it's smaller, and the pointer that we use for the right subarray is K. So we put that here, and instead of incrementing J, we increment K. Now, regardless of which one of these executes, we're always going to increment the I pointer. So I'm going to put that out here. Once this is done, are we finished merging these two halves? Well, definitely not, because this loop is going to run while both of the left and right arrays had values left. But now only one of them will have run out of values by the time this loop is done. We don't know which one it is, so we're going to add code for both of them. So while our J pointer is in bounds, while the left subarray still has some values left, we would then add the values from the left subarray. So pretty much similar to what we did up above, still incrementing the J pointer, and also we're incrementing the I pointer in this case, because this is all we're doing. So this is if the left half of the array still had values. Now I'm going to copy and paste this because we're going to do the same thing for the right half. So I'm going to replace this with K. I'm going to replace this with right, this with K, this with right, and this with K as well. Now, after this loop executes, one of these, only one of these will execute. We don't know which one, so we put both of them here. But this will work out. Maybe there are different ways to write it, but ultimately this will merge the two input arrays together in place by creating a copy of the two subarrays, but it'll merge them in place into the total array that was passed in. So this is the entire code. Now let's run it to make sure that it works. And as you can see, yes, it does, and it's pretty efficient. If this was helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.